Hi, in this video we're going to look at a few examples that involve with first law and the substance is ideal gas. All right. So first one is that a piston cylinder have 5 kilogram. So that's the mass, and it's air, so we know it's ideal gas, and the pressure is 400 kilopascal, and temperature is 30 degrees Celsius. And they said it's isothermal expansion, so we know T1 is going to be equal to T2. And the boundary work WB is 15 kilojoule. It's down by the system. Down by the system. Since it's down by the system, based on the sign convention, that's going to be positive. Then they also said there are 3 kilojoule of paddle work is down onto the system. So that's other type of work. And down to the system, that's going to be negative 3 kilojoule. Down onto the system. Okay. So that's going to be negative 3 kilojoule. Now let's go ahead and thinking about the asking to find out the heat transfer. So find out the Q. So first of all, this is first law. So first law, regardless what type of substance, either is like ideal gas or R134 or water, it doesn't matter. It applies for everything. But is this one, first of all, is this constant pressure? No, because we know it's constant pressure. We're going to use, you could use the equation Q equal to delta U plus work others. So it's not. I'm sorry, constant pressure is going to be Q equal to delta H plus work others. However, it's not. Is this constant volume? If it's constant volume, we're going to use Q equal to delta U plus work others. It's not. It's not. So here you realize it's not constant volume or constant pressure. So if that's the situation, we're going to resort to the most original equation for first law. That's going to be equal to delta U equal to Q minus W. Okay. So now let's go ahead and try to solve it. Delta U. And delta U, this is ideal gas for air. For ideal gas, we're talking about U. For ideal gas, U is a function of a temperature only. And if it's isothermal process, which means temperature is constant, in that situation, our delta U is going to be equal to 0 for ideal gas. Okay, so in that situation, this term is going to be equal to 0. Let's continue to write it down. So we'll have 0 equals Q minus, there are boundary work, there's other type of work. So continue, Q minus boundary work is 15, positive, and other type of work based on sign convention is a negative, so it's minus 3. Then, so Q minus 12 equal to 0. What do we find out for Q? It's going to be 12 kilojoule. So this is how this problem is solved, right? So quick recap on this problem. It is first law. However, it's not constant pressure or constant volume. So we're going to go back to the most original equation, delta U equal to Q minus W. Then this is ideal gas. For ideal gas, trying to find the delta U, we know if it's isothermal process, this U1, U2, it's the same because they are a function of temperature only. So that's delta U equal to 0. Then we're going to use work sign convention. All right, so that's how we solve this problem. All right, for this video, for this second question is a piston cylinder device that has helium. Okay, so for 123, this is a helium. That's going to be ideal gas as well. And the initial temperature P1 is 100 kilopascal. And the temperature T1 is 10 degrees Celsius. And volume 1 is 0.2 cubic meter. And it's now compressed, and it's set a polytropic process. That's going to be a constant. And then the final pressure, P2, is 700 kilopascal, and the temperature T2 is 290. Then they want us to find out the heat loss. Okay, so for this problem, again, it's gonna be ideal. It's gonna be ideal gas because it's a helium, and also it's polytropic. All right, so PVN equal to C. Then it's first law, and this is not constant pressure. Why do I know it's not constant pressure? Because they said it's going to follow the polytropic process. It's not also constant volume. Okay, so in that situation, the first law we are going to use is going to be the most original equation, like the previous problem. Here it's going to be delta U equal to Q minus W. Okay, we need to find Q, and we need to find work. And here, since there's no other type of work, so it will be just boundary work. And now let's get back to thinking about what's a boundary work for polytropic process, right? So you notice all those thermodynamics concepts start to connect them together now. So boundary work for polytropic process is going to be equal to P2 V2 minus P1 V1 over 1 minus N. Okay, so you can look at the previous video on polytropic process boundary work. So then we have the boundary work. Now, do we have N? Does this problem give us N? So we don't even know N. So first we need to find the N. We need to know how to find the N. And we don't know V1, V2 either, right? So there are a few things we need to solve. When you find N, we need to figure out, V1, V2, etc. Oh, we know V1, we need to find the V2. Then we can find the boundary work. Then in order to find our Q, we need to find delta U. Delta U, so internal energy change, and this is delta U for ideal gas. So now we say, okay, there are several ways to solve this. We can go ahead find delta U. Okay, now I think we can figure out this problem. First, let's see if we can find out for V. How do we do that? Because it's ideal gas. Helium is an ideal gas, so we can use P1 V1 over T1 equal to P2 V2 over T2. So from here, we can go ahead find our V2. Let's see. P1 is 100 kilopascal. Our V1 is 0.2 meter cube. Our T1, 10 degrees Celsius, that's 283 Kelvin. We have to change that to Kelvin. P2 is 700 kilopascal, and volume 2 is what we are solving. T2 is going to be 290 plus 273. That gives us Kelvin. That will be answered as 563 Kelvin. Then from here, we can calculate our V2. So our V2 will be equal to 100 times 0.2 times 563, then divided by 283 divided by 700. Let's see what we have. So the answer I have for V2, the volume is 0.0568. That's going to be in units of meter cube. So knowing that, we can, we already know V2, and now I think we can go ahead and tackle this exponent PVN. So then, because it's polytropic process, we know PVN is a constant. In other words, we can put into state 1, P1 V1 N is equal to P2 V2 N. Then, in order to figure out the N, what we can do is, how about V1 V2 power of N? That's going to be equal to P1 P2, right? Cross multiply P2 V to the power of n is equal to P1 times V1 power of n. Then we know that the n is basically equal to natural log V1 V2, not natural log, log with V1 V2, and then this is going to be our P2 over P1. Now let's see if we can solve that. V1 over V2. V1 is 0.2. Our V2 is 0.0568. Then our P2 over P1, let's see, our P2 value is 700 and our P1 is 100. So then we can solve this. Let's see. So from here, I got the answer as n as 1.5467. Okay, that's our n. Now, remember, in order to solve this boundary work, we need to know n, and we also need to know V2. So far, we already got them, right? So we can go ahead and solve the boundary work. Let's see. Therefore, our boundary work for this problem become 1 minus n. And the P2 is again 700. Our V2 is 0.0568. Our P1, where's our P1? Our P1 is 100. And our V1 is 0.2, right? 0.2, yeah. Then we can find our boundary work. So we get a negative value, negative 36.144. And that should be in unit of kilojoule because we are using kilopascal for pressure, right? Now, we get negative value, then think about the sign convention. Boundary work will be negative when the work is done to the system. Is this compressed? Yeah, it said it's compressed, so this boundary work should be negative, so we're on the right track. Now, what we are trying to solve this problem, we're trying to find a Q, and then let's go back our original plan, right? Original plan is first law delta U equal to Q minus W. Then we already figured out this boundary work. Then the next thing we are solving is delta U for ideal gas, okay? How do we figure out delta U for ideal gas? There are so many different ways. We can use the ideal gas table if they have the temperature we have, like 10 degrees and 290 degrees. So let's take a look, see what we have or not. A17 is for air, and this is helium. So we're going to go to the right table. We can look at table of contents. A17 air, nitrogen 18, oxygen next. And guess what? We don't have helium. So then we know method 1 will not work. So we'll have to go resort to other method. So if we are using the average temperature, so the average temperature, do we know the temperature? Yes, we know 10 degrees and 290. So the average temperature will be 150 degrees Celsius. So is there any way, and we are going to use delta U is going to be equal to m. Well, we need to find the mass. Now I just realized that's another unknown. So m times c, make sure here is a CV times delta T. And V here, CV, we're going to use the average temperature. Okay, so so let's go to our table. Now we're going to look at table A2, right? And specifically, it's going to be table A2B. And let's see if we can have a helium table here. Well, guess what? We don't have a helium table. Then the best we can do is we are going to use 300 Kelvin to approximate. So now let's see, how we go step down from different level in terms of preciseness, right? So now we're going to use 300 Kelvin because our temperature averages 150 degree, which is above 300 Kelvin. But now what we can do, here we do have a helium. So we're going to use the helium to solve this, and we're using CV. So it's 3.1156. Okay. So here we realize we cannot do that, so we're going to do MC V at 300 Kelvin, then times delta T. So that's equal to M. I forgot the value we said. 3.1156. Then times delta T. Delta T will be 290 minus 10 degree. And Celsius, so the temperature change in degrees Celsius and Kelvin is the same. Then, again, we're stuck to finding out this mass, right? How do we figure out the mass? Well, then we need to go use our ideal gas equation, right? Right here. So we need to go say P1 V1 is equal to mRT1. Our M is going to be P1 V1 over RT1. And our pressure T1, our pressure P1 is 700 kilopascal. And our V1 is 0.2, I believe. 0.2, yes. And our R and our T1, let's see, T1 is 10 degrees Celsius. That's 283 Kelvin. And our R, we're going to look at table A1. Or you can look at table A2 as well. Helium, the gas, is 2.0769. 2.0769. So knowing all that, we can figure out our mass is in how many kilogram. Let's see. So here the mass I calculated is 0.238. Okay. So knowing that, I think we'll almost be able to solve this problem now. And plug back in. Now we know delta U is going to be, bring back to this mass, 0.238, then times 3.1156. That's going to be specific heat at constant volume at 300 Kelvin. That's approximate. Then times delta T. Then we can find delta U in the unit of kilojoule. Let's see. So here we have 207.79. Now let's go back to our most original equation here. Then what do we have? We have delta U equal to Q minus W, and delta U is 207.79, and we're solving for Q, and the boundary work you calculated is this value. So it's negative 36.144, okay? Then, so be aware this is minus W. This W has sign convention. Its work down to the system is negative. So negative minus negative is basically plus. Yeah, you do want a plus because when you compress something, your internal energy do increase, right? So the sign convention is to follow to make everything number make sense. All right, so now we are going to be able to solve our Q. Q is going to be equal to 207.79 minus 36.144. Let's see what we have here. All right, I didn't realize it was recording here. So anyway, so because of this, P1 is 100 instead of 700, so my mass is 0.034, and my delta U is going to be this value. Bring that in, and so my Q will be finally equal negative 6.48. That's going to be kilojoule. And that negative value, which means the heat is released from the system, right? And I think that's the answer they have here. Pretty close, 6.48 kilojoule. So that's for this problem, and it's actually quite a complex problem. There are many concepts involved. First of all is first law, and we're going using the original equation since it's not constant pressure or constant volume. Then polytropic, so we're going to use polytropic boundary condition, but we don't have everything we need. We need to find the n. So here is how we find the n, and once we find n, we need to go ahead and find the mass here as well, right? To solve it. And actually now I'm looking at, there might be many alternative way to find the P2 V2 minus P1 V1. Here I'm going to just show you. You can explore. This might be easy. 1 minus n, because this is ideal gas equation. So you can use MR T2 minus MR T1, but take MR1 out, so it's basically T2 minus T1. We can, because that's equal to MR T2. This is equal to MR T1 because it's ideal gas. So since you know T2 and T1, and you don't need to figure out the V2 here to figure that out. But however, you still need trying to solve this n. In order to find this n, you know, you might need to find a V1, V2 here as well. Or you can use T1, T2 to, I mean, there's a way to get this as well without finding V1, V2 here. Here I will write it down. So for example, we know this, since we don't know if you don't know V2, here you can use this. What we have is P1 V1 over T1 equal to P2 V2 over T2. So because of that, if I want to avoid finding exact value of V1 V2, I can see V1 V2 is going to be equal to P1 and T2 and P2 and T1, right? Since we know all those, then we find our V1 V2 ratio. So yeah, this might be maybe alternative. I think maybe just a little bit simpler. Okay, then you can find our n, and then we trying to find the ideal gas delta U. That shows our logic. We couldn't find anything on ideal gas table. We couldn't find anything on helium average temperature one either, so we end up using 300 to estimate. That's all for this problem. So it's a good one, and I'll see you next time. Bye.